Hello, this is Zozef, and I'm here to talk about structure property relationships in 4D printed liquid crystal elastomers. So first of all, 4D printing is a process of additively manufacturing an object that changes shape under the influence of an external stimulus like temperature, light, or any other environmental input. Liquid crystal elastomers, or LCEs, are active materials that exhibit two-way shape changes via the transition between the ordered liquid crystal state and the disordered isotropic state. On the right, you can see two photos where the top one shows the photo of a 4D printed heat-activated creeper, and the bottom photo shows the actuation or the two-way shape change of LCEs. The objective of our study is to find various properties of 4D printed LCEs. We also want to find out how these properties depend on printing parameters. Another objective of this study is to print complex structures with controlled actuation. The figure in the middle shows our printing setup. The printing ink, or the LCE ink, consists of Mesogence RMIT2, polymer spacers, photoinitiators. As the viscous ink is pushed out of the small nozzle, shear thinning takes place, and the LCE mesogens become aligned along the printing direction as shown in the figure on the right. Achieving alignment of mesogens is a very important part of 4D printing of LCE, and to achieve this, we experimented with different printing parameters like temperature, printing speed, etc. to find the optimum printing condition. Polarized light microscope images, as shown in the photo on the left, confirm the alignment of mesogens in our printed specimens. We measured the actuation strain of our 4D printed LCE specimens by recording videos of the actuation under the influence of heat, and we processed those videos and images via MATLAB. To find out the mechanical properties of 4D printed LCEs, we conducted tensile tests at 0.1% strain until failure. We also conducted DMA, or dynamic mechanical analysis tests, at 0.1% strain amplitude and at different frequencies. We measured the influence of two printing parameters, printing speed and printing angle, on the actuation of 4D printed LCEs. How the actuation happens is shown in the GIF image on the left. The graph on the left shows that the actuation strain increases with the increase in printing speed. The alignment of mesogens is higher at higher printing speeds, which leads to a higher actuation strain. If the specimens are printed at an angle, they tend to bend while actuation, as shown in the top right images. We found that the radius of curvature decreases at higher printing angles. The tensile test results for specimens printed at different speeds show that the Young's modulus first rises and then drops with the increase in printing speed. The specimens with 0 mm per second printing speed on the left represents a non-printed bulk LCE specimen. It's obvious that the 4D printed LCEs have a much higher Young's modulus compared to the bulk LCE. In case of specimens printed at different angles, the Young's modulus tends to decrease with the increase in printing angle. This happens as the specimens are the strongest along the direction of the printed fibers. When a specimen printed at an angle is subjected to a tensile test, the force is not exerted along the direction of the printed fibers. And so the specimens printed at higher angles exhibit a lower Young's modulus. The results of the DMA tests show that both storage and loss modulus tend to first rise and then drop with the increase in printing speed. Both loss and storage modulus are a lot higher for the 4D printed LCE specimen compared to the bulk LCE specimen. And this is because the printed specimens have a much higher degree of alignment of mesogens. In case of specimens printed at different angles, both the loss and storage modulus tend to decrease with the increase in printing angle. We attempted to use the actuation properties of 4D printed LCEs in various applications to soft robotics. Hinges are a very important part of soft robotics. We manufactured 4D printed bilayer LCE hinges with orthogonally printed layers. The images on the top show different angles of bending generated by different hinges. The bending angle mainly depends on two parameters, hinge width and the printing speed. The graph at the bottom right corner shows how bending angle decreases with the rise in printing speed for a 3 mm wide hinge. The GIF at the bottom left corner shows a self-folding box consisting of 4 hinges. In order for the self-folding box to function properly, all the hinges must generate a bending angle of 90 degrees, which can be achieved by using 3 mm wide hinges printed at 8 mm per second printing speed. Here are some attempts to use 4D printed LCEs in the field of soft robotics. First, on the top left, we have a 4D printed LCE grid that exhibits 2D to 2D deformation. The grid contracts both longitudinally and laterally, as it has printed fibers both along the X and Y axis. Next, we have a flat rectangular LCE strip that turns into a helix with the application of heat. This is an example of 2D to 3D deformation. We achieve this complex actuation by printing two layers at supplementary angles to each other. As we have seen before that specimens printed at an angle exhibit bending, layers printed at supplementary angles to each other create a bending motion in opposing directions, which results in the twisting motion, and thus the helical shape is formed. The pitch of the helix is a function of the printing angle and the printing speed. The turn in the helical shapes become more concentrated and compact with the increase in printing angle and printing speed. At the bottom, we have a 4D printed LCE pyramid that assumes its pyramidic shape from a flat 2D square shape. This is another example of 2D to 3D deformation. The square shape is printed in a spiral square pattern, as shown in the figure on the bottom left corner. This printing pattern programs the material to transform into the pyramid when heat is applied. All of these shape morphings are reversible, and the shape shiftings happen without the help of any conventional means of robotics like electrical or digital signals. So, in conclusion, we came up with the following findings. We found out that the alignment and actuation of 4D printed liquid crystal elastomers increase with the printing speed. We found out that the printing angle creates bending, and the higher the printing angle, the higher the bending. Young's modulus increases with printing speed up to a certain threshold, and then it drops. Young's modulus decreases with the rise in printing angle. And in terms of the viscoelastic properties, both storage and loss modulus present the same trend with respect to the printing speed and printing angle as the Young's modulus. As 4D printing is a nascent field of technology, it's still in its developing phase. Extremely complex structures with controlled actuations have not been achieved yet. But through trial and error, we found out ways to control not so simple actuation patterns. We have printed rather complex structures with predictable and controlled actuation in multiple directions. And finally, here are my references. Thank you for taking the time to listen to my presentation. I hope you have a nice day.